Okay, so hello everyone. So welcome to join our this week Rutgers Inference AI seminar. And today we're very glad to have the researchers from the Microsoft to give us this talk about their great product, the DeepSpeed. And Samyam is a researcher at Microsoft with a background in the high performance computing and systems. He works on developing high-performance structure for accelerating large-scale deep learning training and inference on parallel and distributed systems. And his research results are used in multiple Microsoft systems and products such as Bing Ads, Zoom ML, to improve performance and capacity. He is a co-founder and a system architect for DeepSpeed library, which has enabled orders of magnitude improvement on speed and scale of the deep learning training and inference in the last few years. And as you know, that DeepSpeed has been widely adopted by the AI open source community, integrated to the popular AI platforms such as the Hugging Face, PyTorch Lightning, and used to train and inference a wide range of very large models. The Samyam received his PhD in computer science from the Ohio State University, undergrad in the computer science and physics from Williams College. And also, Jab is a research engineer at Microsoft with a background in distributed systems. And over the past 5 years, he has focused on improving the performance and the scalability of the deep learning training and the inference through the DeepSpeed. And he is a co-founding member of the DeepSpeed team and leads the open source efforts and overall software usability design of the project. And Jab received his PhD degree in computer science from Brown University and undergrad in the computer science from the University of Washington. So now let's welcome our speakers to give us this talk.
Thank you. Thank you both for the introduction and thank you everyone for tuning in and having us. Can you guys see my screen?
Yes, yes.
Okay, perfect. So yeah, today, me and my colleague, Jeff Rasley, we're gonna present our work on DeepSpeed, specifically on efficient trillion parameter scale model training and inference using DeepSpeed. We're gonna touch different features of DeepSpeed connected to this large scale training and AI efficiency at this scale. So let's get started. So first, why large models? Why do we really care about large models? Well, in the last couple of years, the model size has been growing pretty much exponentially, and the reason for that is the larger the model, the better accuracy, the more complex problems that it can solve, and the more compute efficient it is to train this model. My guess is many of you guys have interacted with a large model, even just today when you were talking with Alexa, Siri, or Google Home at the back end. All of those are powered by one or another large language model. ChatGPT, for example, is also powered by a large language model. So the ability and the capability of these models are quite tremendous, and we haven't really saturated the capability of these models. So we actually expect the model size to continue to grow into the future as well. So what is needed in order to train and inference large models? Actually, lots and lots of parallelism. So the table here is kind of showing different parallelisms in types in existence and the model sizes that it can support. What is the maximum parallelism degree that it can support? Is it compute efficient or not? And how easy it is to use. So for example, our standard data parallelism, where we replicate a model across multiple nodes, it's actually quite scalable. You can scale it to thousands of GPUs. You can get very good compute efficiency, and it is very easy to use. You just wrap your model in Torch data parallel or DeepSpeed data parallel, and off you go. However, the limitation is that since it is replicating all the model states, you are limited by a single device or a single GPU memory. So maybe on the newest A180 gig cards, you can fit maybe a 2 billion parameter model. Here, this 1.2 was on a V100 card. So then next we have model parallelism or tensor parallelism, where you split individual tensors across multiple GPUs. When you do that, you need to coordinate data between these GPUs, requires quite a bit of communication, and it only works in the domain where the communication bandwidth is pretty high. So for example, within the node of a DGX pod, where you have NVLink and very high bandwidth. So since you are limited by a single node, the maximum parallelism degree is maybe 8 or 16, depending on how many GPUs you might have within a node. And the model size you can fit is maybe about 20 to 40 billion parameters. So you can combine model parallelism and data parallelism to scale out to multiple GPUs for models of this size. Then we have pipeline parallelism, which kind of splits the model vertically and puts different vertical pieces on different GPUs. Pipeline parallelism has very low communication overhead, so it can scale quite easily across nodes, and you can scale it to hundreds of devices. So you can scale model sizes up to 100 billion or 200 billion with this. And you can now mix and match and combine all of these in different ways so that you can really scale your model size. So for example, if you combine all of these together, we call it 3D parallelism. You can scale to models with thousands and billions of parameters, trillions of parameters. You can scale this on thousands of GPUs. You can get very good compute efficiency. The downside, however, is that this requires significant model code refactoring. As you can imagine, you're splitting the model in all kinds of ways, and the data scientist needs to come in and rewrite the model in that form. And then we have one more line of parallelism that we developed inside DeepSpeed that we call Zero. Zero is a more a more memory efficient form of data parallelism, where instead of replicating data across all the GPUs, we keep them partitioned. We bring the data we need on the fly across all the GPUs, and then we partition them when we don't need it. It's a very natural extension of data parallelism, and it doesn't require any model code refactoring, but it also has similar benefits of 3D parallelism. It can allow you to scale to trillions of parameters, and it can scale to thousands of GPUs. So I guess the main point of this is that you need different kinds of parallelism for training these and inferencing these large models. And if we want to truly democratize and make these large model training and inference accessible to the majority of the AI community, we need easy to use solutions that can support these large model sizes and parallelism degree while remaining highly efficient. And these parallelisms have their trade-offs. So in some cases, one might work the best, in others might. And so you need a system that can bring all of these together. So this kind of brings us to DeepSpeed. At DeepSpeed, we've focused on AI at scale, how we can train large models, inference them, how we can make them fast, how we can make them more accessible, and so on. So I'm going to briefly first give an overview of these different aspects of DeepSpeed. First, in terms of model scale, all the parallelism that we talked about earlier, all of those are either implemented inside DeepSpeed, or they were actually pioneered by DeepSpeed. For example, 3D parallelism and Zero, they first appeared as part of DeepSpeed. If you look at the large language model landscape in the last 2 years, I mentioned earlier, it's been growing exponentially. It's actually grown over 240 times in the last couple of years in terms of model size. Whereas if you look at the AI hardware memory, for example, the GPU memory, that has barely increased by 2.5, 3 times over the last 2 years. And this growth in model size was, in fact, just supported by all these different parallelism degrees. And if we look at DeepSpeed and the maximum model size that we are able to support from the features that we released in the past 2 years, that has actually increased by 4,000 times, allowing us to support models with tens of trillions of parameters, such that the system memory is no longer a bottleneck in training this model. And we've had, because of this, we've had significant, did the slides go back?
Yeah.
Yeah.
Let me try. Oh, Microsoft decided to close my PowerPoint.
Oh no.
Let me try it once again. Can you see my screen?
Yeah.
Okay, perfect. Yep. So so because of the scale that DeepSpeed supports and the efficiency benefits that comes with it, DeepSpeed has been adopted by the community, and a majority of the large models that have been trained today have been trained using DeepSpeed. Now, scaling really large model is actually scaling to really large model sizes is actually pretty easy if you do not care about speed. You can just put everything in disk and everything will run. But we do care about speed. And the only way to train these large models is if you can train it efficiently on the GPU accelerator devices or other device accelerators that are available in today's clusters. So this is a table showing the fastest BERT time back in the days when BERT was one of the largest models out there. DeepSpeed provided the system infrastructure to train BERT in the shortest amount of time. Fast forward to more recent years, the Zero and other technologies inside DeepSpeed allows us to train trillion parameter scale model while achieving super linear scalability across large GPU clusters. And we're going to talk about why we can achieve super linear scalability with DeepSpeed later on in one of our deep dives. Again, on an even newer clusters, the A100s here, we're showing that DeepSpeed can achieve over 50% of the peak throughput of these clusters for model sizes ranging from 175 billion parameters all the way to 2 trillion parameter. So we can support large model sizes as well as achieve very good efficiency and throughput for these model sizes. So one of the challenges with large models is that they require tremendous amount of memory. And generally, when we train or inference these models, we try spreading this memory requirement across a large number of GPU devices. But most data scientists don't have access to a large number of GPU devices. Maybe they have their laptop with a gaming GPU, or maybe they have a desktop with a couple of GPUs. If we want to democratize large-scale AI, then we want to enable that these people can also have access to these large models. So DeepSpeed has features such as Zero Infinity that allows you to leverage CPU and NVMe memory to support these large models without running into efficiency problems. You can still run at a very good fraction of the peak performance of the devices that you have while supporting really large models. Another example of AI democratization is our work on 1-bit Atom. Not all clusters are cutting edge, and they don't have the highest bandwidth interconnect. So 1-bit Atom is a technology that allows you to scale efficiently, even on clusters which has very low bandwidth across nodes by reducing the communication volume. So here, for example, we are comparing the training throughput of BERT fine-tuning with 1-bit Atom on an InfiniBand cluster, and we're seeing a 1.7x throughput on 16 GPUs. On an Ethernet cluster with a much lower bandwidth, we're seeing a 6.2x speed up. And essentially, the key takeaway here is that 1-bit Atom allows an Ethernet-based cluster to perform as efficiently as an InfiniBand cluster, which is a lot more expensive and has a lot more bandwidth. One of the other features of DeepSpeed is compressed training using different compression techniques to enable larger scale sequence length. For example, we have sparse attention that can allow us to support much larger sequence length than possible. We have this technique called progressive layer dropout, which reduces the amount of compute required to train the model without resulting in any accuracy degradation. And one of the more recent lines of work that we've been exploring is DeepSpeed data efficiency library, where we apply techniques on the data and how the data is exposed to the model so that you can get to a similar quality model with less data, so effectively reducing the time it takes to train the model, making the training process more efficient. And now, once you've applied all of these techniques to train your model, how do we inference them? As we talked about earlier, the model sizes have continued to increase, and now the models range from a few 100 million parameters to hundreds of billions of parameters. They can also be dense or sparse. The scenarios in which we are using these models can also be widely varied. We might be using these models in a production scenario where you would need real-time inferencing, where you want your latency to be a couple of milliseconds, or you might be using the model in an offline processing scenario, where you don't really care about the latency, but you care primarily about throughput and efficiency. So given all these scenarios, how do we, and all these different model sizes, how do we get the best possible latency and throughput for these scenarios? And for this, we have DeepSpeed Inference, which combines systematically a diverse set of optimizations so that we can tackle each one of these scenarios. And at the time we released this work, we achieved SOTA latency and throughput across the entire large model inferencing landscape. So the next part that we want to make sure that we can enable efficient AI is also usability. Jeff, I'll hand it to Jeff to talk about this. And then after that, we're also going to take a deep dive on some of the key technologies inside DeepSpeed that enables some of these high-level overviews that I've given.
Excellent. Thanks, Samyam. Let's see. So yeah, in terms of usability, we take this part quite seriously. If you can click to the next animation there, Samyam. So we essentially only have a few lines of code change to enable DeepSpeed on various PyTorch models. So you could actually access all these sort of scalability aspects that Samyam has covered already with just a few lines of code change. And what's great about this is we also have tight integrations with both Hugging Face and PyTorch Lightning and several other open source kind of sister frameworks, if you will. And in this example here, you can kind of see how this is done with Hugging Face. There's essentially just you pass in a DeepSpeed config and kind of a DeepSpeed flag into an existing kind of Hugging Face trainer, and this can unlock all sorts of different features that we have in DeepSpeed. Similarly, with PyTorch Lightning, they have kind of a plugin called like a DeepSpeed plugin that allows you to access all these features. And next, we are essentially infrastructure agnostic, so you could use this on kind of your local machines, maybe you have in your lab, or VMs in the cloud, or services like Azure ML, and this sort of thing. Okay, next slide. So for a concrete example here, we'll dive into a bit more detail about this later, but on the left side, we see kind of a typical Torch NN module. We're essentially wrapping that in our DeepSpeed initialize, which is kind of like a DDP-like wrapper with a DS config, but then the train loop is mostly unchanged here. We just kind of do our forward, backward, and step. On the right side, you can see an example of a DeepSpeed config where a user is specifying maybe they want an Atom optimizer and they want to maybe offload their optimizer or param states to CPU or NVMe. This is essentially it to be able to enable zero infinity like features that we'll talk about next. One of the things we want to call out in terms of kind of open source impact of the framework. So we released this in the spring of 2020. And since then, we've had a little over 4 million installs on pip. So today you could just pip install DeepSpeed, for example. Had over around 200 different unique contributors from inside Microsoft, outside Microsoft, Amazon, like all sorts of different folks have kind of contributed to DeepSpeed. We also see around 1,000 different public packages have dependencies on DeepSpeed. So these are things like Hugging Face, like we mentioned earlier, PyTorch Lightning, if you've used or heard of Luther AI, Mosaic ML, these sorts of frameworks kind of include dependencies on DeepSpeed and integrations with them. We've also seen lots of different companies and national labs being sort of using DeepSpeed for various efforts, either in open source repos or models that they've trained. Yeah, all right, next slide. So yeah, let's dive into zero infinity. This is in terms of breaking the GPU memory wall for deep learning training. Next. Okay, so yeah, in the past 2 years, what we've seen is model size has increased around 240x. I think Samyam touched on this a little bit earlier, but while the amount of GPU memory is actually only increased by around 2x, right? So it's not really any longer possible to fit sort of these large models on a single GPU. And the deep learning training systems have actually evolved to combine multiple different forms of parallelism, such as tensor slicing, pipeline parallelism, our zero technique, to leverage an aggregate GPU memory in a cluster to support training large models. So given this large model training landscape, we have sort of 3 questions that typically arise here. So one is, how do we sustain the growth in model size, specifically, especially as we reach this sort of GPU memory wall, and where even sort of aggregate device memory is no longer sufficient to fit these large models for training. And the number 2 here is once these large models are actually trained, how can we make them more accessible for fine-tuning scenarios? So without requiring hundreds of GPUs that most modern sort of clusters don't necessarily have. The third is, how does a state-of-the-art technology like 3D parallelism uses tensor slicing and pipeline parallelism? It requires kind of major core refactoring, which is often error-prone and extremely painful and tedious for data scientists to apply. Is there a way we can kind of simplify that pipeline to actually be able to enable large-scale model training? So in the next couple slides, we'll talk about how we can address some of these challenges with zero infinity, and we can start by talking about this GPU memory wall. So actual modern kind of clusters, like in this kind of focus, we're looking at like NVIDIA DGX2 machines. These were the V100 machines. This was also called like superpods. They have heterogeneous memory systems, but the aggregate GPU memory accounts for only actually like 2% of the total storage and memory in the system. So in this plot on the right, we see like GPU memory, CPU memory, and NVMe storage is quite large in aggregate. So from a memory perspective, can we actually support, or from a memory perspective, a single node can actually support training a 20 billion parameter model with just GPU memory. But if we can actually extend this to use both CPU and NVMe memory, we can actually support training a trillion parameter model. So this means models like GPT-3 could actually be fine-tuned on a single node. So how can we leverage some of this non-GPU memory? Can we simply just extend the existing parallel technology to leverage the CPU and NVMe memory? So let's take a look at our candidates here. So we can use data parallelism. However, this replicates a lot of the memory states and causes a significant memory explosion. We could use tensor slicing, but this doesn't really scale beyond a single node due to communication overheads that are required for this approach. Next is pipeline parallelism, but as we've discussed, there's lots of different sort of code refactoring requirements here. It's a deep integration into the model. The next is, can we actually use our zero redundancy optimizer? This efficiently scales across nodes up to trillions of parameters, and we actually don't require any sort of model code refactoring. So let's do kind of a recap of what zero is. So zero stands for this zero redundancy optimizer. So it provides a memory efficient form of data parallelism. And in data parallel training, each GPU kind of stores a replica of all the different model states. However, in zero, each GPU only stores a mutually exclusive subset of parameters, entirely removing all these different redundancies. So during training, when a parameter is actually needed, it's just broadcast from the owner GPU of that parameter to all the other GPUs across the GPU interconnects using like something like InfiniBand. So next, how can we extend this idea of zero to use non-GPU memory? Can we simply kind of offload the model states to NVMe and move them to GPU only when they're needed? In theory, this would take us kind of beyond this memory wall, right? But in practice, it actually has severe efficiency limitations. So based on our theoretical analysis for the training here with 0, to be efficient on a DGX2-like system, we would need between around 25 to 60 gigabytes per second bandwidth to read and write the parameters and gradients, depending on kind of what batch size are actually used. But the NVMe peak bandwidth on a DGX2 is around 28 gigabytes per second, which is, well, on the lower end, but maybe there. But since each parameter is owned by a unique GPU, and 0, the bandwidth from NVMe is limited by PCIe link bandwidth between the GPU and the NVMe memory, which in this case is only 12 gigabytes per second. So this severely restricts the efficiency of 0 compared to running kind of directly on GPU. So can we do better? And in this sense, what we've designed is the system called Zero Infinity. So Zero Infinity, actually what we do here is partition each parameter across all data parallel GPUs before offloading to NVMe. When a parameter is needed during that training, each of its partitions is moved to the owner GPU using multiple PCIe links in parallel. Then to reconstruct the full parameter on each GPU, it uses an all-gather operation instead of a broadcast. We'll see this in action. We have a nice little animation we'll show you shortly to kind of show you how this works. But note that this system design kind of allows NVMe to GPU bandwidth to increase linearly with the number of data parallel GPUs. So on a single DGX2, we can achieve near peak NVMe bandwidth of around 28 gigabytes per second on a 64 node cluster, sort of a massive 1.8 terabytes per second bandwidth, which is far beyond kind of what we need in this scenario. So next, let's see Zero Infinity in action. Click on the animation there. Awesome. So in this case, we can just kind of watch this. So we kind of break it on the left there. We kind of see the process of where we're going and with respect to forward, backward, and update in the training. So right now we're in the forward. So we're all gathering the parameters and computing activations. You can see on the bottom there, the yellow is kind of signifying the different parts of the model, the different layers in the model, let's say. And then the bottom right, there's a legend showing the different colors. So we see like the activations green, parameters are yellow, and gradients are orangish. So now we're in the backward. We're all gathering the parameters, computing gradients, and then the reducing and scattering of those gradients across GPUs. And then finally, third phase is in terms of parameter updates. So parameters and gradients are moved to the CPU. We update the parameters, and then move the parameters to NVMe. Excellent. All right, so before we look at the evaluation results for Zero Infinity, we'll do kind of a quick recap of the 3 questions we asked earlier about large model training landscape today. So how do we support, or how do we continue to support growth in model size beyond the GPU memory wall? 2 is how do we make large model training more accessible on fewer GPUs? And 3 is how do we simplify large model training by avoiding model code refactoring? Oops. All right, so by leveraging CPU and NVMe memory, Zero Infinity actually is built to sort of shatter this GPU memory wall by supporting model sizes like 50x larger than possible with GPU memory. So like a 32 trillion parameter model that requires 25,000 GPUs to fit for training can now actually only fit, or can fit with only just 512 GPUs instead. So this also enables Zero Infinity to fine-tune these GPT-3 size models on a single DGX2 instead of 16, allowing for much broader access to these larger model fine-tuning scenarios. So I do want to point out that the aggregate NVMe memory bandwidth is roughly 500 times slower than the aggregate GPU memory bandwidth on the clusters. So the natural question to ask here is, are we sacrificing throughput efficiency for a model scale? And we're really sort of delighted to share here is that despite using a 500x slower memory, the system design for Zero Infinity is able to achieve excellent efficiency and scalability, kind of on par with state-of-the-art GPU memory. Solutions like 3D parallelism when used with kind of reasonable batch sizes. Finally, I want to conclude by saying that all of this can be kind of enabled without any major code refactoring. It's all kind of hidden behind this DeepSpeed library. So the DeepSpeed config that I showed earlier, and then we'll talk about a little later as well, is essentially just allows you to kind of turn on and off these features relatively easily. In conclusion, when I think of we think of Zero Infinity offers a kind of a promising path towards training multi-trillion parameter models in the future. At the same time, makes kind of large model training more accessible and simple. And next, I'll hand it back to Samyam to talk about a mixture of experts work.
Thank you, Jeff. Okay, so next we'll talk about DeepSpeed support for a mixture of expert models. One of the fundamental questions that we're curious about is, can we achieve the next generation of model quality on the current generation of hardware? What do I mean by that is, if we look at some of the largest models that have been trained today, for example, the Megatron Turing NLG 530 billion, it took us 60 days to train this model over a bit more than 2,000 NVIDIA A100 GPUs. Now, if we want to train the next generation of dense models like this, let's say we increase the scale by a factor of 5 to a 2.5 trillion parameter model, that would take over 300 days on the same amount of resources, almost a year. That's a significant time, making training models at this scale impractical. So is there a way to reduce the time to train models of this scale, or at least produce models that would have the quality of this scale? One promising path towards this is MOE-based models. MOE-based models have been around for a while. G-Shard, switch transformers shared how these massive sparsely gated models can work really well compared to their dense counterparts and can be trained much more quickly. So what exactly are these mixture of expert based models? So if we look at a dense model, in the forward and backward pass of this model, each token is processed by every single parameter in the model, which means as we increase the size of the model, we also require more computation. And that is the reason why when we increase the size of the model, the training time increases, or the iteration time becomes slower. For an MOE-based model, each token is only utilized or processed by a subset of parameters based on a gating function, which means that we can keep increasing the model size, but that doesn't really increase the amount of computation required to process a particular token. So we can increase the model size at the same compute cost. So therefore, if we use an MOE model, perhaps we can get a higher quality at a sublinear cost and still be able to train these large models in a reasonable time. So MOE is quite promising in that regard, but it is also has some limitations. For example, when we were initially looking at this work, the scope of MOE was quite limited. We didn't know if MOE-based models would work for natural language generation tasks like the ones that this Megatron Turing NLG or GPT-3 were trained for. So we actually looked at how these models would do for these tasks. So here what we're showing is we're comparing a 1.3 billion parameter dense model. We're comparing that with a 1.3 billion parameter dense model with an MOE added to it. And this MOE has 128 sparsely gated experts on top of this. And then we are also comparing all of this with a 6.7 billion parameter dense. The computational requirements, or the compute in the 1.3 billion dense and the 1.3 billion MOE, 128 billion experts, are essentially the same, whereas 6.7 billion dense has 5 times more compute requirements. So if we look at the loss curves, clearly 1.3 billion dense does much worse, but they're like towards the end of the training, both the MOE and the 6.7 billion dense model achieves nearly same validation loss. If we look at some of the downstreaming tasks, we see the validation loss actually translates to the downstream performance as well, where we do see that this 1.3 billion parameter model with MOE performs similar to the 6.7 billion parameter dense model, despite requiring 5x more compute and achieving 5 times higher throughput. So what is the catch here, though? The main catch is that while the 6.7 billion dense model has about 6.7 billion parameters, the 1.3 billion MOE model actually has a total of 52 billion parameters. So we've actually increased the model size by 8x using MOE in order to achieve computational efficiency. So in order to get quality parity of a 6.7 billion parameter dense model, we needed the MOE model to have about 8 times more parameters than the dense one. So that brings us to the second problem, this massive memory requirement. If MOE models require 8 to 10 times more memory than the quality equivalent dense models, how do we support training these models? For this, we have a line of work which combines different forms of parallelism to train these large MOE models efficiently. The key behind scaling these MOE models is actually expert parallelism. We've touched on data parallelism, tensor slicing, pipeline parallelism, and zero. And expert parallelism is now a completely new form of parallelism where we keep the experts of an MOE model across multiple nodes. Each one of these nodes or each one of these devices are going to be trained using something like data parallelism, or we can use tensor slicing or zero. But when the tokens are about to get to the MOE layer, we use something like an all-to-all operator, so that the tokens can be grouped together based on the experts. So all the tokens that goes to a particular expert will be grouped together and sent to the GPU or the device that contains that expert. So with expert parallelism, we can support MOE models. Now, by combining expert parallelism with data parallelism, zero, or even tensor slicing, as well as zero infinity, we can scale the model size dramatically, and we can get all the benefits of zero infinity that Jeff talked about for MOE-based models as well. And in DeepSpeed, currently, we support all of these different parallelism combinations to allow us to support really large MOE model training. With that, we are able to scale the MOE model size by 8x compared to state-of-the-art infrastructures in terms of model size. So for example, on 512 A100 GPUs, we can support training an MOE model with 3.5 trillion parameters. Another way to look at the same thing is we can now support large MOE models that could only be trained on massive number of GPUs, now with 8 times fewer resources. Then let's say we've resolved the scope, we've resolved the memory requirements, but now these models are just really massive. How do we actually do inference on them? Are they going to be really slow to inference because of the model size? So to address this, we designed a highly scalable MOE inference system. The goal of this system is to scale MOE inference beyond tensor slicing. Tensor slicing allows us to leverage the aggregate GPU memory bandwidth within a node. But since these models are so large, in order to run them with a reasonable latency, we need much higher aggregate GPU memory bandwidth and compute than what is available on single node. We want to be able to scale this across hundreds of devices. To do this, we perform 3 optimizations. First is a combination of parallelism that allows us to go beyond the bandwidth requirements of tensor parallelism and go across nodes. We do this by combining tensor data and expert parallelism. Then we perform multiple parallelism coordinated optimizations to reduce the communication overhead that leverages tensor and data expert parallelism in a way which where we interact with the properties of these parallelism to minimize the communication volume. And then we have kernel optimizations that allows us to maximize the bandwidth utilization per GPU device. So let's take a look at some of these in a bit more detail. First, in MOE model, we observe that each token is only processed by at most a single expert. And we also notice that each token can be processed independently of all the other tokens. So with expert parallelism, we are already grouping tokens based on experts, and we can run these experts in parallel and coordinate them using all-to-all. Now, if we compare the communication volume of expert parallelism versus tensor parallelism, we do see that expert parallelism incurs a much lower communication volume than tensor parallelism. So this is a good candidate to allow us to scale beyond a node where tensor parallelism cannot go. Then for the parameters that are not MOE, we can still use tensor parallelism within a node. However, now we have a discrepancy. We are able to scale MOE parameters across multiple nodes, whereas the non-MOE parameters, we're now limited within a node. So to address that, we bring in data parallelism, where we scale the non-MOE parameters across node with data parallelism, and that doesn't require any additional communication volume. So essentially, we're scaling the non-expert parameters with a combination of data and tensor parallelism, and we're scaling the MOE parameters with a combination of tensor and expert parallelism. Then in terms of communication optimization, we perform all the generic communication optimizations like NUMA-aware. We use optimized communication libraries like SYCL. However, the problem with doing all-to-all is that as we increase the number of devices involved in it, the latency of the all-to-all grows linearly with the number of devices. So there is a massive overhead when we try to scale this to a large number of devices. So in order to optimize this, we use parallelism coordinated all-to-all. Now, if we look at a situation where we are using tensor slicing as well as expert parallelism, tensor slicing actually replicates data among all its GPUs. So when you do an all-to-all with tensor slicing enabled before that, you end up with an all-to-all where the result is also replicated in some sense. So we leverage that idea of replication. So instead of initially keeping the data replicated, we perform a partitioning and remapping of the data so that when we do the all-to-all, the data is no longer replicated, but the communication volume is also reduced because we've avoided the replication in the first place. So that's the core optimization in our DeepSpeed MOE inference library. So now let's take a look at the performance. With DeepSpeed MOE, as we increase the number of GPU devices when we inference an MOE model, we actually see a superlinear scalability in terms of throughput. Whereas for a dense model, the best we can achieve is just linear throughput. The reason why this happens is as we increase the number of devices, we are able to significantly reduce the amount of memory required per device, and hence we're able to significantly increase the batch size per device as well, allowing us to get better throughput as we increase the number of devices. Then in terms of latency, DeepSpeed MOE allows us to scale to hundreds of devices. Here we're showing a 52 billion parameter MOE model's latency scaled all the way to 64 GPUs. And we can see that the latency is still coming down even after we've gone across over 4 nodes here. So with DeepSpeed MOE, we're able to achieve both low latency as well as superlinear throughput increase as we increase the number of GPU devices. So here is a more broader comparison where we are comparing the latency of DeepSpeed MOE and comparing that with a PyTorch-based MOE implementation for model sizes ranging from 107 billion parameters all the way to 2 trillion parameters. And we're seeing that DeepSpeed MOE reduces the latency by up to 7.5x. And the fascinating thing here is that even a trillion parameter model, MOE model, can be inferenced in just under 25 milliseconds, which is real-time latency. If we compare that to a quality equivalent dense model of size 200 billion, even though the dense model is 5 times smaller, the fastest inference that we can do for that model is only 50 milliseconds because we don't have expert parallelism there to be able to scale it beyond a single node for the dense model. So now, an interesting comparison that we would like to do is how does the latency of a quality equivalent dense model compare with that of an MOE model? So what if we take two models, one is dense and small, the other one is MOE based, it's sparse, but it is much larger, but they produce the same quality. How do the latency of these models compare? If we look at it just from a PyTorch-based implementation, the MOE model is significantly slower. However, if we apply DeepSpeed MOE, the MOE-based model is actually significantly faster. So with DeepSpeed MOE, we are able to make inferencing of these massive MOE models practical in real scenarios. So now coming back to our initial question, can we enable next generation of AI on current generation of hardware? So here we're just trying to push everything to scale here. Let's say we want to compare a GPT-3 dense model, which is 175 billion parameters. It's a pretty big model with a quality equivalent MOE model with 1.5 trillion parameter models. And earlier during the training part, we showed that we can achieve quality equivalence as long as the model size is roughly about 8x larger. So that's why we're comparing a 1.5 trillion with a 175 billion parameter model. Once again, here we're seeing that with DeepSpeed MOE, the quality equivalent MOE model can actually be inferenced 4.5 times faster than the dense model, despite being much larger in size. And we can inference it with 9 times higher throughput, making inferencing models at this scale not just possible, but also practical. Now, coming back to the question we were asking earlier, are we able to also train the next generation of models on current generation of hardware? And so initially we were talking about this 530 billion parameter model taking 60 days. If we were to train a quality equivalent MOE model using DeepSpeed MOE, that would require training a 2.12 trillion parameter MOE model, but we would be able to do that in 12 days. So now if we want to train the next ambitious model of size 2.5 trillion parameter dense model, then for a quality equivalent model, we would still be able to train that in the same time it took us to train the Megatron Turing 530 billion parameter model. So through DeepSpeed MOE and the work that we did here, we're actually able to show that we can train with 5 times higher compute efficiency and achieve qualities of dense models that would just simply not be possible if we were to train them as dense model on the current generation of systems. To learn more about this line of work, we have a blog called Advancing MOE Inference and Training. I would encourage you guys to check it out. And next, would like to hand it back to Jeff to talk about some of the usability aspects of DeepSpeed.
Thanks, Samyam. All right, yeah. So how do we kind of install and use and kind of get started with DeepSpeed? Let's go ahead and next slide. So from a software sort of architecture standpoint, we like to think about DeepSpeed in kind of this stack. So the lowest level, we have kind of our hardware. Next level is some sort of training infrastructure. So this is either like Azure ML or like AWS or local machines or all sorts of things. And on top of that, we have some low-level libraries. These are things like provided by NVIDIA, like CUDA and Nickel. On top of that, we have frameworks that are written maybe in PyTorch or like Python, like PyTorch, TensorFlow, these sorts of things. The first kind of introduction here is sort of DeepSpeed Ops. In the green, this is kind of what DeepSpeed's providing. But at the very, very top, we have kind of a user model in blue that then kind of interfaces with DeepSpeed via various APIs. So like DeepSpeed Initialize for training, like I think we briefly talked about earlier, there's kind of a DeepSpeed configuration JSON or dictionary. We also have kind of a special initializer for inference only kind of scenarios. But then sort of the DeepSpeed APIs then interact with the DeepSpeed runtime for very sort of adding in different training and inference optimizations, where we help kind of you deploy and data partitioning, model partitioning, and all that kind of fun stuff. Then the next piece are DeepSpeed ops. So these are kind of lower level operators that we've written for DeepSpeed in C++ and CUDA to provide kind of accelerated computation or communication and these sorts of things. Next. So the key here is that some of these all these optimizations kind of are on top of existing training and inference frameworks like PyTorch, and we're also kind of agnostic to the types of training or inference infrastructures that you may be running your systems on. Next. So let's dive into a couple different examples. So this first example is you kind of have an existing user code. This is, we do primarily or only kind of support PyTorch currently, but this is typically in PyTorch you would write your models using a Torch NN module. This is from the docs on the right. Next. And then the user code sort of modifications to add DeepSpeed in. You can wrap your NN module in potentially other pieces, like if you're using custom optimizers, learning rate schedulers, data loaders with this DeepSpeed initialize wrap. And then next, you can kind of optionally add this Python argument parser in, so you can pass in maybe different DeepSpeed configuration JSONs if you want to kind of tweak those for your running. And then the returned kind of model or engine that's returned from DeepSpeed initialized, you can then perform your forward, backward, and sort of optimizer parameter updates with respect to that. So in addition to this, we also provide something called our DeepSpeed launcher. So this helps kind of launch training or inference scenarios across multiple different nodes. So this DeepSpeed kind of binary, you kind of loop in whatever your training script is, and whatever arguments you might need for that kind of client entry point, and then pass us a DeepSpeed configuration JSON. So this example is like a C410 example here. You just kind of do DeepSpeed, and what this does is it's able to kind of deploy this training job across all your distributed nodes. Next, and then handles actually propagating different environment variables you might need and data partitioning. And the most important part is that it then seamlessly kind of incorporates all of these different system optimizations that we've been talking about today. So a little bit more concretely on the left, this is an actual GPT-2 model. I think this was from NVIDIA's Megatron framework a few years ago. So the model is created as like this GPT-2 model, maybe the number of layers that the user wants. To do kind of FP16 level training, you need to wrap that model again to kind of cast it into half precision, then wrap it again with a distributed data parallel to do the gradient averaging, kind of support all the fun things for data parallel training. Construct not only then your Atom optimizer, but then also a special kind of optimizer for stability reasons on FP16. And then do your kind of forward, backward, and parameter updates like this on the bottom left. But then when adding DeepSpeed, you essentially still create the model and the optimizer in the same way. You don't care about kind of FP16 or FP32 training. DeepSpeed can handle that for you. And then you wrap this in the DeepSpeed initialize here. And then now the next one click. There we go. So then we do kind of a very similar forward, backward, and update step, but now all with respect to this model engine that was returned. Yeah. More details, you can kind of see some of these examples in our Megatron DeepSpeed repo, or also in our DeepSpeed repo itself. And in terms of it enabling zero, like it's very similar to what I showed earlier, but this is a kind of a concrete DeepSpeed config JSON on the right, where we're kind of enabling different types of FP16 training, and then just a basic zero optimization true, which would enable kind of 0 stage 1 type optimizations. So there's a couple of good links here in terms of if you want to get started. We have a sort of this hello DeepSpeed example in our DeepSpeed examples repo. That's a good way to get started. It has a lot of good documentation of kind of how you can kind of play with this and turn on and off different features. We also have lots of inference optimizations that build off of kind of Hugging Face provided models and optimize those. So you can check those out. Both of those are in our DeepSpeed examples repo. Next. And want to stress, like, you can run this anywhere. You can run this on Azure, of course, is something we would prefer, but you can also run this on your local infrastructure or other cloud providers as well, and on AMD and NVIDIA, I should say. But yeah, we of course have an affinity here towards Azure ML, so yeah, please check that out if you haven't already. And we're in the process of releasing additional examples of kind of how to use this on AML. And in conclusion, thank you all so much for for your time. We have a couple asks, I suppose. If you could, it'd be great if you could star our repo on GitHub. We would very much appreciate that. You can also check out more details on GitHub and our DeepSpeed AI website. We also have kind of a newly revived kind of Twitter account called Microsoft DeepSpeed. Feel free to follow us there. We're going to be using that for kind of release new papers and new releases of DeepSpeed and kind of a central communication channel for things going forward. With that, I think we can probably have time for some questions if anyone has any.
So, can I ask some questions? Sorry.
Please do.
Yeah, Tommy, go ahead. Yeah, you can ask questions.
Oh, yeah. Thanks. Yeah, I'm a user of the DeepSpeed. Thank you for the great work and impressive
Awesome.
work. Yeah. So I have a few questions. So one question is, I'm trying to understand the code. So because you mentioned in your talk, say, I mean, there's no need for code refactoring when you use the DeepSpeed. However, I do have a problem, for instance, based on my understanding, I mean, DeepSpeed, for instance, for the traditional DeepSpeed, you use a module-based hook in order to for instance, do something. Yeah. So the question is, it looks like some functions. For instance, if I model f dot linear, then the module-based hook cannot be triggered. So how do you handle this case? If you still want to do the 0-3, I mean, then yeah, I try to understand what's the strategy you are using to do that.
You mean instead of using modules, if you use torch functionals, then you were worried about the hooks not being triggered properly.
Yeah.
Right?
Yeah, I guess some hooks will be not triggered properly. So are you try to turn this 0-3 to 0-2, or how to handle these things?
So I think as long as if you're using a torch functional and that functional is using a parameter, that's when we need to worry about the hooks getting triggered. And as long as the parameter is registered as part of its parent module, the hook should trigger okay.
I think so, yeah.
Yeah.
If you see something specific like that, though, yeah, it's, have a concrete example, if you're to file an issue, and then you can also email us. I think Bo has our email. Feel free and remind us, or kind of call out the issue, I guess, via our email too.
Okay.
Happy to take a look.
And if there's a scenario that we haven't considered that we're encountering, we'll be more than happy to take a look and work it out together with you.
Yeah, I think when you, for instance, when you model, you call torch nn.functional, for instance, .linear, for instance, a simple example, and then a module-based hook will be not triggered. From my understanding, I mean, I take a look at your code. I think what you're doing is you didn't do the sharding in the beginning, and then you effectively turn the 0-3 to 0-2 in this case, because you just don't shard those specific layer.
But the F linear is going to be on with respect to some inputs, right? Those inputs maybe are either parameters or it depends on what those inputs are. If those inputs are created as not parameters, I guess they wouldn't be under the purview of 0-3, but the parameters themselves would be. So there's hooks, our hooks are kind of parameter specific. They are possible, there are part of the modules themselves, mostly because the parameters are just part of those modules. And so those hooks fire in terms of doing those all gathers or doing all the required things there. But yeah, happy to take a look further in a issue though.
Okay. Yeah, thanks. I guess I have another question. It's more a high level question. So I know that for instance, a lot of people think in order to train on a huge model, we should use maybe PP plus TP instead. So yeah, I'm trying to understand what do you think of this question? Do you think we could just use the zero-based DP and plus the PP, or I mean, or what's the best configuration you think should be if I trying to train, for instance, 1 trillion like parameter, or even bigger? Yeah.
You want to take this, Jeff? Or do you...
You can go ahead. Go ahead.
Yeah. So I think it really depends on. First, it's an excellent question. It's a question that we've debated a lot as well. I think at the end of the day, it matters on what kind of cluster you are running this on. If you're running this on a cluster which has really low bandwidth across nodes, then zero scalability is also limited by data parallel scalability. It can only scale as efficiently as data parallel training. So your batch size is so small that even data parallel cannot scale, then you're going to run into scalability issues if you run this with zero. 3D parallelism, pipeline parallelism, and tensor slicing combined together, it incurs very little communication overhead across nodes because of how pipeline parallelism works. So if you are running on a low bandwidth cluster and you have a model already refactored in a way for 3D parallelism to work, then that would probably be the ideal solution. Whereas if you're running this on a very high bandwidth cluster like a DGX2 superpod, then both zero and 3D parallelism are going to give you very similar efficiency, but you avoid all the model code refactoring and the pain and debugging that comes with 3D parallelism.
Okay. Yeah. Thank you. Yeah, I guess like I do like simple experiments like by my own, but not like a very big model. It looks like, I mean, I guess like, anyway, we have to use pipeline maybe, or maybe not, but like if we use pipeline, then the question tends to compare with the tensor slicing parallelism and then like the zero. So what I found out is like when I use like a small number of for instance, cores, like 2 core or like 2 GPUs or 4 GPUs, looks like the tensor parallelism looks like it has a better performance. But if we use, for instance, 8 or even like bigger, then like zero definitely has a big win later. Yeah.
Within a node where the bandwidth is high, tensor parallelism can actually work pretty well, but tensor parallelism requires so much communication that as soon as you go across nodes, its performance will come down.
Very bad. Yeah. Super bad. Yeah.
Yep.
Right. Thank you. Yeah.
Yep.
Thanks.
Thank you for the questions.
Yeah, thank you.
Other questions from our audience? So actually, I have several questions. Yeah. So first, so you mentioned that so the DeepSpeed, so actually, so it can be run different kind of infrastructure then, and both like the AMD and NVIDIA GPU. So I'm curious about that. So right now we have some even more emerging hardware like the Cerebras, right, and like the Habana and so on. So I was wondering, so whether the DeepSpeed consider to further to extension to those that are emerging hardware, because you introduce that right now you are also the DeepSpeed is used like in those the national labs, and as I know those the national labs the Argonne, they also are right now exploring the use of those the new hardware. So I was wondering how about the integration of the DeepSpeed to those the computing platforms. Yeah.
Started doing some of these integrations, not entirely. So like I think we've had some really good collaborations on the open source side with Intel, for example, and AMD on kind of adding support for non-NVIDIA GPUs. I think that's the first good kind of start, either on NVIDIA or like Intel like GPU type hardware, like Habana or these sorts of things, and then also like Intel CPUs. So definitely keep an eye, I think, of the space there on as we kind of expand to support other types of accelerators. But yeah, I definitely think that's an interesting area to explore further.
Yeah, absolutely. And we have been in multiple conversations with the Cerebras team as well. no plans to integrate yet, but I think from just an idea and optimizations standpoint, we are on continued conversation. So if an opportunity presents that we can extend that to DeepSpeed, we are definitely open to. And we started this effort to abstract out accelerator devices in DeepSpeed so that integration can happen not just through DeepSpeed, but anyone who has a new accelerator device can implement the interface that we provide, so that would be supported by DeepSpeed automatically.
Okay, thank you. And another question is about the potential support for the heterogeneous system. So right now, I assume that all of your examples or the experiments around that like the 256, the same type of GPUs, right? But in some cases, like for example, in the federated learning and the different users, they have to come different types of the GPU. Some maybe from NVIDIA, some from the AMD, or some even for the different type of NVIDIA GPUs. So whether the DeepSpeed consider to support this type of the infrastructure scenario?
We have seen some users do this. I think it kind of does work, especially like if they're all GPU based accelerators. I think this should work. I mean, you're going to potentially see all sorts of crazy imbalances in terms of compute, especially if you're using really old generation, or like some features might not be available in some versus the other, which could cause issues. But like fully federated or decentralized kind of training, I think it hasn't been traditionally our focus. Like I know that there's this work like Petals and stuff that we're doing amazing things in that space to check out. But like, yeah, I do apologize. I have to run for another meeting here.
Okay.
I need to run, but
okay.
Thank you guys for having us.
Thank you so much.
This was fun.
Thank you so much. This is a really very wonderful talk. Thank you. But also thank our audience to attend today's talk.
Absolutely.
Absolutely.
Thank you.
Thank you.
Thank you. Have a wonderful day. Bye.
You too.